So welcome once again and welcome to next lecture of physics optional. Okay, so let's learn about binding energy per nucleon. But before that, I would like to tell you something that if you, in case you haven't watched the previous lectures, then you should surely watch the previous lectures by going to the link in the description. Okay, there is a link in the description. If you go to that link, just click on that link and start with the first blue colored thumbnail. Okay, just go to that link, scroll down, and then you will find the first blue colored thumbnail. Start from there, then you will surely understand everything. If you haven't watched the previous lectures or if you don't know the ABC, then you are not going to understand the current lecture. Okay, so binding energy per nucleon. So as the name suggests, it should be the binding energy divided by the total number of nucleons, and the binding energy divided by total number of nucleons, as A represents your total number of nucleons. Okay, your mass number is basically your total number of nucleons, right? So EB is the binding energy of the, it is the total binding energy. EB is your total binding energy divided by total number of nucleons. Total number of nucleons means your total mass number. So total binding energy divided by total number of nucleons or total mass number is equal to your binding energy per nucleon. Okay, so it is basically your average binding energy. So EB bar is equal to EB divided by A. So binding energy divided by mass number of the nucleus or binding energy divided by total number of nucleons, both are same. So binding energy per nucleon is given something like this. Sorry, and it is also called as average binding energy, where your binding energy as found out in the previous lectures. Okay, if you have watched the previous lectures, then you must know this thing very well, that your binding energy is given something like this, that it is Zmh plus A minus Zmn minus mx, where mh is the mass of hydrogen atom, Z is your atomic number, means the total number of protons, A minus Z is the total number of neutrons, Mn is the mass of each neutron, and mx is the isotopic mass of the nucleus. Okay, isotopic mass of the atom, I would say, rather than the nucleus. Okay, isotopic mass of the atom rather than the nucleus. So mx is the isotopic mass of the atom. All these things we have found out in the previous classes, and all these things in the bracket, all these things in the bracket are given in atomic mass units. As all these things in the bracket are given in atomic mass units, as all these things in the bracket are given in atomic mass unit. So after multiplying that thing by 931 mega electron volt, after multiplying that thing by 931 mega electron volt, we get the binding energy. This we have already found out in the previous lectures. Example, now over here one example is there, binding energy of H12. Okay, what is this? This is your deuterium. Okay, we are finding out the binding energy per nucleon of deuterium over here, not deuteron. There is a difference between deuteron and deuterium. Okay, there is a difference between deuteron and deuterium. Let me tell you that, suppose this is your nucleus, suppose. Okay, and in this nucleus, suppose two protons, one proton, sorry, not two protons. Suppose there is a nucleus and there is one proton and one proton and one neutron in this nucleus. And suppose this is the nucleus, so it will be H12 clearly, right? So if it is a nucleus only, then it is deuteron. If it is nucleus only, then it is deuteron. But if it is something like this, that atoms or electrons are also there, means it is an atom. So if it is a nucleus, then it is deuteron. If it is consisting of both electrons also, then it is deuterium. Then it is deuterium. So this thing has also been clarified in the previous lectures. So binding energy, now over here we are neglecting the binding energy of this, the binding energy on account of these two electrons. The binding energy on account of these two electrons we had already ignored while deriving the derivation, while we were making the derivation. We had ignored the binding energy on account of these two electrons. So that thing has been ignored in this formula. So this can also be called as binding energy of deuterium or deuteron, both. Okay. So binding energy of H12, deuterium or deuteron, whatever you say, but there is a difference between deuterium and deuteron, which I told you. So binding energy of H12 is 2.2 mega electron volt. So its binding energy per nucleon, its total binding energy is this much. 2.2 mega electron volt is the total binding energy. But the binding energy per nucleon will be EB bar is equal to 2.2 divided by 2. This is the atomic mass number. So total binding energy divided by atomic mass number will be equal to binding energy per nucleon. It will be equal to 1.1 mega electron volt per nucleon. Now we will plot a graph between binding energy per nucleon as a function of A for various nucleus. We want to plot a graph between them. So the graph is shown on the next page. So graph looks something like this over here. The graph looks something like this. Over here it is binding energy per nucleon on the y-axis. On the y-axis there is binding energy per nucleon, and on the x-axis there is atomic mass number. On the x-axis there is atomic mass number, and on the y-axis binding energy per nucleon is there. So clearly this graph shows a trend of this kind, that initially when the mass number increases, initially with a slight increase in mass number, even a slight increase in mass number initially implies a very large increase in the binding energy. Okay, there is a steep increase. There is a steep increase in binding energy per nucleon for a small change in mass number. For very low atomic mass number nuclei, there is a steep change in binding energy per nucleon, even for a small value of A. Even a small decrement or increment in A causes a large change in binding energy per nucleon for very small atomic mass numbers. But then suddenly there is a little bit of drop. Okay, over here, if you study the nuclear shell model, then you will understand that why there is a little bit drop over here in the binding energy per nucleon. Okay, so over here there is a little bit drop in the binding energy per nucleon with increase in atomic mass number. With increase in atomic mass number, there is a little bit drop over here. Then again, with increase in atomic mass number, the binding energy per nucleon again starts increasing. It keeps on increasing. Okay, so the rate of increase decreases. Okay, rate of increment decreases, but it keeps on increasing. But the rate of increase decreases. Then it reaches a maxima. Binding energy per nucleon reaches a maxima. It reaches a maxima at Fe56. Okay, so corresponding to that maxima, the binding energy per nucleon is of the order of 8.8 mega electron volt per nucleon. This is 8.8 mega electron volt per nucleon. Okay, this is per nucleon. What is this? Mega electron volt per nucleon. Okay, so over here it reaches a maxima, and this maxima is 8.8 mega electron volt. Okay, so this is the thing. So these lighter nuclei, as they have lower value over here, there is very low value of binding energy per nucleon, right? Over in this area where there is a very low value of binding energy per nucleon. So the nuclei over here, in order to attain stability, the nuclei over here in this particular region, in order to attain stability, undergo fusion. undergo fusion. Okay, they fuse with each other. So it is called fusion, means two smaller nuclei, two lighter nuclei will combine to give a heavier nucleus. Two lighter nuclei will combine to give a heavier nucleus. Okay, and energy is released in this process. So this is called as nuclear fusion. So in the nuclei which lie in this particular area of the binding energy graph, the nuclei which lie in this particular region of the binding energy per nucleon graph, means in this particular region, they will easily undergo fusion. Then over here the nuclei are somewhat stable. This region up to 50 to 200, up to 50 to 200, this region, this particular region, the nuclei are somewhat uh, although the stability somewhat decreases, a little bit it decreases at a slow rate, but more or less it remains constant. Okay, so stability in this particular region between atomic mass number 50 to 200, in the region of atomic mass number 50 to 200, the stability remains somewhat constant. Then this region, this particular region, the stability has decreased very much, about 200, about 200 atomic mass number, about 200 atomic mass number, the stability has decreased very much. So in this particular region of the graph, the binding energy per nucleon is very small. So in order to attain stability, the nuclei over here undergo fission. Okay, they will get undergo fission, means a heavier nucleus will break down into two smaller nuclei. A heavier nucleus will break down into two smaller nuclei, and as it will break down into two smaller nuclei, some energy will be released in this process. Some energy will be released in this process. So the nuclei over here in the region about atomic mass number 200, above atomic mass 100, above atomic mass number 200. Okay, above atomic mass number 200, above atomic mass number 200, the nuclei will undergo fission in order to attain stability, and they will fuse into two nuclei. They will fuse into two nuclei whose binding energy will be somewhere around here. Whose binding energy will be somewhere around here. They will fuse into two such nuclei. Okay, so this is the thing. And around here, around Fe56 and all these things, means up from 50 atomic mass number, from 50 atomic mass number to 200 atomic mass number, the nuclei are almost stable. Okay, are almost stable, with some few exceptions are there. Some few exceptions might be there, but usually these nuclei are stable, and usually these intermediate nuclei neither undergo fission nor fusion. Usually these usually these intermediate nuclei neither undergo fusion nor fission. Okay, so this is the thing. Now some facts have been written over here, that EB by A means binding energy per nucleon greater. If it is greater, then the nucleus is more stable. We have already learned this. For Fe2656, the atomic number of iron is 26 and the mass number of iron is 56. So EB bar means binding energy per nucleon is around 8.8 mega electron volt per nucleon. It has the highest value. So the nucleus of iron is highly stable. Do not confuse it with the chemical reaction. Okay, the chemical stability is very different and nuclear stability is very different. When I say that the Fe56 iron 56 nucleus is stable, I just mean that the nucleus is stable. I don't mean that the atom is stable. Atomic stability depends on electrons. Atomic stability depends on electronic configuration. Nuclear stability depends on nuclear configuration. Okay, so Fe56 nucleus is highly stable, highest stability in the periodic table. Fe56 nucleus is highly stable, but that does not mean that its chemical reactivity will be low. No, chemical reactivity is least for the noble gases. Okay, helium is the least reactive element. Okay, according to chemical reaction and electronic configuration, helium is the least reactive element, but we are talking about nucleus here. So the nucleus of iron is highly stable. Okay. So the nuclear stability and the chemical stability, they do not have any relation with each other. So do remember this thing. So Eb bar, that is the binding energy per nucleon of iron 56, is 8.8 mega electron volt per nucleon, which has the highest value. That is iron 56 is the most stable. The curve is approximately constant for 30 to 170. You can see over here. For 30 to 170, over here somewhere it will be 30, right? Over here somewhere it will be 30. Okay. So over here it will be 30 somewhere. Over here it will be 170 somewhere. So the curve is almost constant for 30 to 170 over here in this region. For 30 to 170 the curve is almost constant. Okay, not purely constant but almost constant. So the curve is approximately constant for atomic mass number 30 to 170. For atomic mass number 30 to 170 the curve is approximately constant, indicating that the nuclear force is a saturated force, which is explained by short range of nuclear force. What does it mean by saturated force? You know this very well, that while forming a nucleus, okay, while the formation of nucleus, these nucleons will be situated something like this. Okay, the nucleons will be situated inside the nucleus something like this, right, in the form of compact packing. Compact packing. Okay, the nucleons will be there inside the nucleus something like this. So now the nuclear force nuclear force, its range, the nuclear force range is of the order of 10 to the power minus 15 meter. Okay, so nuclear force acts if the distance between the nucleons, is of the order of 10 to the power minus 15 meter, only then the nuclear force will act. But suppose if I keep on increasing the size of the nucleus, suppose I have such a small nucleus, then the distance of 10 to the power minus 15 meter will be maintained. 10 to the power minus 15 meter will be distance will be maintained in this. So these will be bound together. Okay, but over here if I increase the size of the nucleus, then the distance between these two nuclei, suppose I want to find out the distance between this nuclei and this not nucleon. Okay, I want to find out the distance between this nucleon and this nucleon, then clearly this distance will be 10 to the power minus 14 meters, suppose, right? So it is different, the distance is altogether different. So the nuclear force is short range force, so the attractive force will act in something of this area only. Okay, the nuclear force, the attractive nuclear force will act over this area only. So attraction will be in this area only. So this area will instead experience repulsive interaction because of electrostatic force. Okay, so nuclear force is a short range force. So that's why the thing is like that. That the curve is approximately constant for this, indicating that the nuclear force is a saturated force, which is explained by short range of nuclear force. I told you the reason. If we split a heavy nucleus into two medium-sized ones, each of the two nuclei will have more binding energy per nucleon than the original nucleus had. The extra energy will be given off. Now let us understand this. If we break a heavy nucleus over here, if it undergoes fission, then it will be in the form of two smaller nuclei, and these two smaller nuclei will lie somewhere over here. So energy will be given out in this process, because these two nuclei will have binding energy over here, which is greater binding energy. So greater binding energy implies more stability, and as these two are more stable than this, so some energy will be released. According to thermodynamics also you have learned this. So it will be an exothermic process. So if we split a heavy nucleus into two medium-sized ones, each of the two nuclei will have more binding energy per nucleon than the original nucleus had. The extra energy will be given off. in the form of heat or something. So it will be an exothermic process. What does this imply? This clearly implies that it will be an exothermic process. Exothermic process. Okay. Binding energy curve drops at high mass numbers. Okay. This clearly over here you can see that for high mass numbers, or for high atomic mass numbers, the binding energy curve drops. Okay, the binding energy curve drops for high atomic mass numbers. Binding energy curve drops at high atomic mass numbers, which implies that the nucleons are more tightly bound when they are assembled into two middle mass nuclei rather than into a single high mass nuclei, right? Rather than a single high mass nuclei having mass greater than 200 atomic mass number. Okay, suppose a nucleus has atomic mass number 200. Okay, and if it breaks down into 100 and 100, then these two intermediate nuclei of 100 and 100 mass numbers will have greater binding energy per nucleon than the original 200 nucleus. So the stability will increase. So binding energy curve drops at high mass number, which implies that nucleons are more stable. Nuclei are more tightly bound when they are assembled into two middle mass nuclei. More tightly bound means more binding energy per nucleon. Okay, more is the binding energy per nucleon, more are they tightly bound. So more tightly bound means more binding energy per nucleon. So more binding energy per nucleon when they are assembled into two middle mass nuclei rather than into a single high mass nuclei. The reason is very simple. The reason is this only, because if I assemble it into intermediate nuclei, okay, so suppose if I assemble into a very small nucleus, so in case of a very small nucleus, only three interactions will be there. Suppose it has three nucleons, so only three nucleon interaction is there. So this is a very lighter nuclei, so it will have low binding energy because of low interactions. So it will lie something over here. But an intermediate nuclei, look at an intermediate nuclei. This is an intermediate nuclei. So in this intermediate nuclei, the distance between the nucleons is not so large. So there will be sufficient interaction. So this intermediate nuclei will lie somewhere over here, because the intermediate nuclei will lie somewhere over here. But as soon as I increase the mass number, suppose I increase the mass number to such an extent, very large number of nuclei are there, large number of nucleon are there. Okay, so what will happen is that in this large number of nucleons, clearly the nucleon over here and nucleon over here, they have a very large distance. Very large distance means the nuclear force will not act properly between them. As the nuclear force will not act properly between them, so clearly they will experience electrostatic repulsion. Okay, so clearly this nucleus will be highly unstable because it has very high mass. So it has undergone a saturation. So the nucleus which we discuss right now lies somewhere over here. Okay, very high atomic mass number. So binding energy curve drops at high mass number, which implies that nucleons are more tightly bound when they are assembled into two middle mass nuclei rather than into a single high mass nucleus. Okay, energy is released in the nuclear fission of a single massive nucleus into two smaller fragments. Okay, the drooping of the binding energy curve at low mass number implies that energy will be released if two nuclei of smaller mass number combine to form a single nucleus of higher mass number. New nucleus has more binding energy per nucleon. This is very clear. The drooping of the curve. What does this mean? The drooping of the curve, like this, the curve is drooping. The curve is drooping over here. Okay. So very lighter nuclei are also unstable. That's what it means. Okay. The drooping of the binding energy curve at low mass numbers implies that energy will be released if two nuclei of small mass number combine to form single nucleus of higher mass number. New nucleus has more binding energy per nucleon. Okay, this is self-explanatory. For example, in this particular process of fusion, this is what? This is basically your fusion. So in this particular process of nuclear fusion, H12 and H12 fuse to give He24. So energy is released, 23 mega electron volt of energy is released in this process. This process is known as fusion. Two lighter unstable nuclei combine to form a heavier stable nuclei. Okay. Now there is a one question: calculate binding energy per nucleon of alpha particle. We have to calculate the binding energy per nucleon of alpha particle given the mass of 1h1 atom, this much, mass of neutron, this much, mass of He24 atom, this much, and 1 AMU is equal to 931 mega electron volt according to Einstein energy mass equivalence relation. This is the thing. From delta E is equal to delta mc square. From that we got this. Okay. So binding energy per nucleon we have to calculate. So first of all calculate the binding energy. So binding energy is given like this. The formula you have already learned. Then we have to substitute the values in the place of Z. What will you put in the place of Z? In the place of Z you will put 2. Okay. So you have put 2. Then mass of hydrogen atom. It is given in the problem. So mass of hydrogen atom is given in the problem. Then atomic mass number minus atomic number. So atomic mass number is 4. From where do we get it? The atomic mass number is 4 minus the atomic number means the number of neutrons. So number of neutrons is over here. Then the mass of each neutron is also given in the problem. Then isotopic mass of alpha particle is also given in the problem. So the isotopic mass of alpha particle is also given in the problem. Okay. Alpha atom basically means helium atom. Okay, because it is given mass of atom over here. So over here also it is mass of atom according to the formula which we have already derived in the previous sessions. So 4.002604. Okay. So this is the thing. Then 931 mega electron volt will be multiplied. So this is clearly your binding energy. Now this is the binding energy, not per nucleon. We have to calculate the binding energy per nucleon, and over here we have found out the binding energy only. So in order to get the binding energy per nucleon, we have to divide by the total number of nucleons. The total number of nucleons will be equal to the atomic mass number, and as the total number of nucleons will be equal to the atomic mass number, so A will be equal to your 4. So EB divided by 4 will be there. So mega electron volt per nucleon. So 7.075 mega electron volt per nucleon, which is the binding energy per nucleon. So in this way you can find out the binding energy per nucleon of alpha particle. Okay. And over here you note one thing, that we have neglected the binding energy on account of electrons. While derivation only we had learned this. While deriving the formula of binding energy, we had already learned that we neglect the binding energy on account of electrons. We had already learned this. So this thing you have to keep in mind while learning the formula and while solving the problems. Okay. So this is the thing. Hopefully you like the lecture. If you like the lecture, then please do subscribe to our channel and please press the like button. Thank you very much.